So hi, for this video we will be discussing Laplace transforms. So Laplace transform, the knowledge of Laplace transforms is very important in engineering. Okay, so this is because Laplace transform provides easy and effective methods for solving many problems arising in different areas of engineering. It can also be used in solving linear differential equations, okay, so which we have previously discussed in our lessons before. So we can compare later on the traditional solution and the solution of Laplace transforms, and then we can see that Laplace transform really provides easy solutions, okay, of those problems, those type of problems. Okay, so for Laplace transform we have the symbol, this one, so it looks like a cursive letter L. So the Laplace transform of a function f of t, okay, so is equal to f of s. Okay, so what Laplace transform actually do is it converts a function from the time domain to the s domain. Okay, so from time, okay, to s domain, or the frequency domain. Okay, so that's what Laplace transforms do. Okay, but it can also be applied to other problems as well, okay, not involving time and frequency. Okay, so let the function of time be f of t, and then its Laplace transform is f of s with a capital letter F. So Laplace transform means we will integrate, okay, the function of time multiplied by e raised to the negative st dt from 0 to infinity. Okay, so later on we can see that we have formulas, okay, for Laplace transforms, but for the meantime, so we'll derive some of those formulas, okay, the easier ones, and then from there, so we can just memorize the Laplace transform formulas. Okay, so first example, so we have find the Laplace transform of f of t is equal to 1 when t is greater than 0. So here we are asked to find the Laplace transform of 1. Okay, so from the formula, so the Laplace transform of 1 is equal to the integral of f of t, which is 1, e raised to the negative st dt, okay, from 0 to infinity. Okay, so you can see here we have an infinite limit, so therefore this is an improper integral, and to write improper integrals properly, so we must replace infinity with another variable. So let's say a, and then write the notation of the limit. So instead we will be writing it as the limit of the integral of 0, so infinity is, we will replace it with another variable, so let's say a, okay, and then the integrand. So if we simplify this, so this is simply e raised to the negative st dt, okay, so where a approaches to infinity. Okay, so next is do simple integration. So this is integral of exponential function, so we have recall that the integral of e to the u du is equal to e to the u plus c. So in this case our u is negative st, okay, and our du must be negative s dt. Okay, so as you can see, for us to apply this formula, so that du should be the complete differential of u. Okay, and as we can see, the differential part here is the differential part should be negative s dt. Okay, so as you can see, we have a missing factor of negative s. So therefore, we must write negative s, okay, in the differential part. And then, since we write negative s in the integrand, then outside the integral sign, we must write the reciprocal of negative s. So which is negative 1 over s. So this will now become the limit of the integral of e raised to the negative st. The differential part should be negative s dt. Okay, so limit from 0 to a as a approaches to infinity. And since we write here negative s, then outside the integral sign, we must write the reciprocal of negative s to balance it out. So the reciprocal of negative s is negative 1 over s. Okay, so we can now integrate this. So this will become the limit as a approaches to infinity of negative 1 over s. The integral of this now will become e raised to negative st. Okay, limits from 0 to a. Okay, so remember here that we are treating s as a constant, by the way. So substituting a and 0 to t, okay, and then upper limit minus lower limit. So this will become limit, say, approaches to infinity of negative 1 over s. Substituting the upper limit, so this will become e raised to negative s times a minus e raised to negative s times 0. Okay, so evaluating, so this one for the second term, so it will become e raised to 0, and e raised to 0, we know that that is equal to 1, right? So this is equal to 1. However, on the other one, so we have the limit of e raised to negative s a as a approaches to infinity. So it will become e raised to negative infinity, okay, or it will become 1 over e raised to infinity. So we can rewrite this as limit of negative 1 over s. So we can rewrite this as 1 over e raised to sa minus, we know that that is 1, okay, as a approaches to infinity. Okay, so if a approaches to infinity, the value of this fraction will become 0. So because we'll have 1 over e raised to infinity is infinity, then 1 over infinity is its limit approaches to 0. Okay, so therefore what will remain is negative 1 over s times negative 1. Okay, or the Laplace transform of 1 is simply 1 over s. Okay, so this is now the Laplace transform of 1. Okay, in the time domain, its value is 1. In the s domain, its value is 1 over s. Okay, so let's have another simple example. So for our next example, so find the Laplace transform of f is equal of f of t is equal to e raised to a t, where a here is a constant. Okay, so again, using the definition of Laplace transform, so the Laplace transform of e raised to a t is equal to the integral of e raised to a t for the f of t times e raised to negative st dt, okay, from 0 to infinity. Okay, so we can simplify the integrand, so we can combine them. So since this is multiplication, all we need to do is copy the base and then add the exponents. And then for the limits, so this is with infinite limits, therefore we will replace infinity with another variable and then write the notation of limits. But since we already have a here, so we can use another variable. So let's say the limit of the integral of from 0 to b, okay, as b approaches to infinity. So simplifying this, so this will become e raised to at minus st. Okay, and then simplifying this, so we can factor out, we can factor out t, okay, and also we will factor out -1, so that the factor will become s minus a. So this will become the limit of the integral of e raised to s minus a times t dt. Okay, from 0 to b as b approaches to infinity. Okay, so integrating this, this is integral of an exponential function again. So where our u here is negative s minus a t. Okay, so therefore our differential part must be negative s minus a dt. Okay, so we have a missing factor here of negative s minus a. So therefore we must write that, okay, to complete the differential, and then write the reciprocal of the factor that we multiplied with the integrand. So it will become limit of, let's provide some space, integral of e raised to the negative s minus a t, and then multiply it by negative s minus a dt. Okay, so we have written here negative s minus a, so therefore outside the integral sign we must write its reciprocal. So negative 1 over s minus a. Okay, from 0 to b as b approaches to infinity. Okay, so since the differential part is now complete, so therefore we can now apply the formula for integration of exponential function. So this will become the limit of negative 1 over s minus a times integral of this will now become e raised to the negative s minus a times t from 0 to b as b approaches to infinity. Okay, so next is we can now substitute the limits b and 0, so we will substitute it to t. Then it will become the limit of, so write the factor outside, so 1 minus s minus a, so this will become e raised to negative s minus a times b minus e raised to negative s minus a times 0. Okay, as b approaches to infinity. Okay, so similar earlier, so the first term will become 1, because we have e raised to 0, so this will become 1. This one we can rewrite this as the limit of negative 1 over s minus a. We can rewrite this as 1 over e raised to s minus a times b. Then we have here minus 1 as b approaches to infinity. Okay, so if b approaches to infinity, so then this will become e raised to infinity. The denominator will become e raised to infinity, and e raised to infinity is 0. So e raised to infinity is equal to infinity. Then 1 over infinity, its limit approaches to 0. So therefore, what will remain is negative 1 over s minus a times negative 1. So therefore, simplifying, the Laplace transform of e raised to at, okay, is equal to positive 1 over s minus a. Okay, so this is how the formulas for Laplace transforms are derived. Okay, and for solving Laplace transform, so we don't actually need to derive each Laplace transform. So there is an easier way, and that is memorizing the Laplace transforms of common functions. Okay, so those functions will be flashed after this. So these are the some common functions, okay, and their Laplace transforms. So for formula number 1, the Laplace transform of 1 is 1 over s. So we have derived in our first example. So number 2, we have the Laplace transform of t is equal to 1 over s squared. Formula number 3, t squared, we have its Laplace transform is 2 factorial over s cubed. Formula number 4, if we have t raised to n, where n is equal to 0, 1, 2, 3, 4, 5, and so on. So all positive, okay, and 0. So its Laplace transform is equal to n factorial over s raised to n plus 1. Number 5, we have a gamma function. Okay, so that is its formula number 6. Formula number 6, we have derived this in our second example. So the Laplace transform of e raised to at, that is equal to 1 over s minus a. And the other formulas from 7 to 12. Okay, so kindly memorize those formulas because we will be using those in our next lessons. Okay, so good luck.